Alright, hello. This course is intended to be just a kind of experiment where I will try to explain some math spontaneously. The particular aim of the course is just to give a short introduction to the basics of linear maps. That's a topic within linear algebra. Okay, let's try to start it. To consider linear maps, we actually first need the notion of a vector space because it's maps between vector spaces. So first, let's define a vector space. So a vector space is the following quadruple: vk plus dot, where v and k are certain algebraic structures and v and dot are certain operations. Right, so what is v? V is an abelian, and that is a commutative group with the operation plus. What does that entail? Well, first of all, that's supposed to be at, right? Plus, let's maybe do it with such sense. Plus is closed on V, which means for all VW that are in V, we just get that V plus W is also always in V. Right. That's the most basic property. Then we get plus is associative on V, plus is associative. And that means that for all V, W, X in V, we actually get V plus W plus X is same as V plus W plus X. And here I have noticed that I have forgotten something very important. What is actually our plus? Plus is just a map which goes from V cross V to V. This is basically the condition of being closed, but we better define it in the mathematical notation, in particular because of the use of this bracket notation. It has directly to do with how it is defined, and namely recall, as I said, plus is a map. Map is a basic definition that I actually supposed to be known, but let's just recall it. It is a rule with two given sets. Let's call the sets D and W. D is called domain, and let's call this rule F. D is domain of F, and W is value space of F. Well, a rule with two given sets, DEW, that assigns to each D element in D, a W element in W, which operation of assignment we write, or the result of assignment we use them interchangeably, which we write of D equal W. So it's just a generalization of the definition of a function on the real numbers that takes values in the real numbers. So now this plus, for example, is a map that takes a pair. This is the set of all pairs of the vectors in V. So an element of this would be just an element like V1, V1, V2 would be element of this. Where V1 is any vector in V and V2 is any vector in V. Right. V1, V1 would be also possible, so it could be same vector. No problem with that. So, and that goes now in V. It takes such a pair and it assigns to it some vector in V, which we write in V1 plus V2. So then the meaning of this becomes clear. V plus W is namely same as plus evaluated at VW. We have a map, we have this pair. Actually, should write this because we evaluate our map at a pair, but it's just a convention that we usually don't write double brackets if it is clear what is meant, right? And then to the result of this, we actually apply plus and take this result with x, right? And here we could have in general something different because here we first apply plus to this w and x, which is written here. I already adopted a convention. And then we apply plus to v and the result of this. Well, an example where it would not be the same would be, for example, the composition of maps. Well, what good example could I give you? Yeah, you just have to know that the composition of maps. Actually, sorry, composition of maps is of course an example where it works just fine. It is associative. just by definition of composition, it's easy to see that it is associative. But where associativity would not work? This is an interesting question. Well, let me think a little bit. As I said, it's just a spontaneous video, so don't expect me to have thought it through in advance. Okay, but let me think. Let me think. Clearly, our usual examples just don't work because, well, because they simply don't work. So the first things that one would came up with, they just would not work. Right. I know. We take something elementary, we just take division in real numbers. So just consider as counter example to associativity always working by any operation, this counter example. Let's make it a 4. And if you first compute 4 divided by 4, and then you divide it by 2, it's definitely not the same as 4 divided by 4 divided by 2, because this gives you a 2, and this gives you 1/2. We consider this operation in real numbers, right? We could also consider it in rationals, but it doesn't matter. The main point is that is not associative. So this here is important. Our plus could be anything, right? So plus is not necessarily the addition as we know. For now, it's just an operation with the properties that we have stated until now. It's not all properties, but for now, we could just encounter something funny, which just wouldn't have property of associativity on some structure. But for vector space, we need a non-covered property. Oh, let's continue. Plus is associative, and there is a neutral element of addition which we customarily just call 0. There's always a neutral element of addition. It's just called 0. Addition called 0, having the property that for all v in v, we just get that v plus 0 is 0 plus v, and you can guess what it should give. It should give v again. Right, and do not be fooled. This we have defined now. I could call this element A. This element is defined by its property, and we claim we want to have its existence. So we suppose that it should exist for us in order, this is one of the properties that should be satisfied for us in order to call something a vector space. So it's not like this works like 0 because we call it 0. No, we call it 0 because it has the main property of 0, right? All right, this is a fine distinction. You should be aware. Right. And finally, for each V, element V, it exists and is actually unique by this quantifier with this exclamation mark. We just denote a unique existence. So if this is existence and if there is an exclamation mark, that means there exists and it is unique. Exists a unique vector minus v, and again, we just denoted minus v. It's just the notation. It's not like because of minus, this vector works like that. And you see, like what? You can probably guess. There is such a vector that this vector plus this vector is same as this vector plus this vector, and this is equal to 0. So it works like a minus, not because we call it a minus. So we call this vector minus v because we want this vector to have these properties, and for that is just a suitable name to call it minus v, right? All right. And of course, we will adopt notation like v plus minus w just by real numbers for grown-ups. We'll adopt notation that just define it like, well, the other way around actually. So yeah. We just define it as that, right? It's just a definition. V minus W will mean V plus this vector minus W, which is the special vector for minus W. Oh, yeah. Okay. And a billion, as I said, that just means uh, the group is a billion or commutative if, well, you can guess, if plus is commutative, that is if plus is commutative. It is, and from now on I probably will omit those for all quantifiers when it's clear that I'm talking about all vectors. W, v plus w is equal to w plus v. Oh, okay, I'll write it by differently now. Well, vw and v. All right, let me see. Right, this is a group. But this is not all for vector space. For some reason, we have also our field, and that's not for nothing. That was oh, that was V is an abelian group. That was the first component. Second component is K is a field. It is K. Let's call it like well, let's call it, I don't know. That like that. And that's supposed to be a curved plus, okay? It is K curved plus star is a abelian group just like we finished above with respect to curved plus. It is simultaneously an abelian group with respect to Parisian star, and the neutral elements of those operations we just call, you see, neutral element is in the definition of the group, right there above. The neutral element is here. So we call the neutral element, how you understand that it is a neutral element, because the star is kind of multiplication and curved plus is kind of addition, or it is what is supposed to be rows of that. And the 1 plus, of course, 0 plus the neutral element of this curved addition. And why I don't use plus and multiply it here, because I want to distinguish those operations from the operations in the vector space, because it's operations in the our structure working with our objects and so on. So we should distinguish it just for now. In the subsequent considerations, we'll get used to it and be clear there's different things, but for now let's distinguish it. And this and distributive laws. Out and test. Okay, distributive laws, what's that? Oh, that is for all again, but clearly it is for all A. So just the distributive laws from school, but with our funny operations. That's supposed to be a star, right? I'm not always accurate by writing these operations down. Yes, that's okay. So, and the other distributive law, well, what would you expect? Just see. A plus B. Actually, we don't need it because we have commutativity, but let's just write it down. Of course, that's curved plus. Of course, that's curved plus. And that's, oh, since we have commutativity, you see that C multiplied by A is same as A multiplied by C. And of course, we adopt the usual convention. So here you could put brackets, but we just assume that when I write something like this, that means multiplication binds stronger than the addition. Right? B multiplied by C, I can be free there because I just have assumed commutativity already, and we have to assume commutativity Boolean group with respect to plus curved with respect to star, because that is in the definition of a field. So that is a field. So we have introduced our abelian group as a structure participating in the definition of vector space. We have introduced a field as a structure participating in our definition of a vector space. And now let's find out what they have to do with each other. K is a field. And finally, the last ingredient, dot, is scalar multiplication. So the field is sometimes called field of scalars. That's why scalar multiplication. Dot as a scalar multiplication on V, and that is just a map that goes from cross V to V, such that, and this thing has following properties. Now one, I could also call it 1K because it's one field. So yeah, like maybe for future could write it down like that. And then it's clear which operation this is the operation of a field. And of course, if I don't try it for all, it still means for all. So for all V in the vector space V, right? Just too lazy. Such that holds, and of course again, okay, I maybe should write it here because we now have objects from two different structures. So let's write it. This is in K, and this is in V. So first compute that in the field, and then we apply the scalar multiplication in the vector space. And pay attention. Okay, I should pay attention myself. This is in the field, so this is star multiplication, and this is multiplied now by the scalar multiplication, and this is some kind of pseudo associativity. Here we have lambda, and here we have dot. So yeah, pay attention where which multiplication is applied. In particular, there was no transformation of star into dot. You should not think in these terms. You should just understand what is applied to what and where which operation works, which actually what actually makes sense, right? Okay, and then the two pseudo distributive laws. Again, here when I write such Greek letters, so Latin letters like lambda, beta, or whatever, and write V, and clearly lambda and mu just in the field, and our V is in vector space, and again, of course, it should hold for all elements of K and for all elements of V. Right, and here lambda is of course a scalar, and V plus W are elements in our vector space, and we get, pay attention in particular that the scalar in the multiplication is usually always written left, or always on the same side. At least we will write it probably always left. Could be written always on the right, but it's just a convention to not mix things up, right? Okay, so this is the definition of a vector space. We recall it's just an abelian group with a field such that there is scalar multiplication with certain properties defined for this abelian group and this field. This is the absolute definition of a vector space. As you can see, that's different than at school. At school, you actually have considered the particular example of the vector space I.III, that is the vector space that is given, whose elements are given by vectors with 3 real coordinates, or maybe 2 real coordinates, or plane, and you have just called it vector space, or you have defined everything in terms of this particular vector space. We don't go this way. We define it really generally because we want to have those definitions as mathematicians have them so that we can work with them properly. And those mathematical definitions, they work in all that generality. Yeah, because you can do more awesome stuff when you have such general definitions. All right. Well, what now? Now I should give you some examples, right? All right. Examples of vector spaces. Well, let's just take a field. Consider a field K, and now let's just do some weird stuff. Just take this as the usual notation for addition, multiplication. We mean by plus addition, by times we mean multiplication, right? Uh, uh, and well, consider the vector space K plus, that's our V now, right? Because that's a group, we can take this group, right? No problem with that. It is a Boolean, just by definition of a field. We take as our field KVK itself, no problem. There it was different letters, but it could be same set, no problem. If it just has structure of a vector space, the first element of the quadruple, the second element has a structure of a field, there are no additional requirements, and we just take its own operations where pay attention plus is really plus in K, and dot is really the operation in K, so that we just define the scalar multiplication to be the actual multiplication of the field, which is possible because the elements, the scalars and the vectors are actually from the same set on which the multiplication is already defined. So in our words, lambda multiplied by k is now special case where we have just defined lambda to be in k, k to be in k, and this dot is defined on this k as the structure, having the structure of the field that's just in k. So, of course, we should give a more concrete example because now it probably freaks you out. But yeah, so what I mean is just more concretely, more concretely. R plus, so just real numbers with addition, right, is a group. R as a field, right? The operation plus and multiplied were lambda k, just multiplication, real numbers. You can check carefully that it is indeed a vector space. Please don't get confused by the structures. You should just develop this view that can see objects from different perspectives just based on what they structurally are or what purposes they can structurally serve in the context, right? You should not think, well, this is same thing and we have already that as a field, so it can't be a vector space. So don't think that. And so you should just carefully understand what is what in what context and how and why it makes sense in the particular context, right? So that was the first example. So in particular, like rational numbers Q are also a vector space, and well, what else? Complex numbers C are vector space, and they are R vector space, that is with field, could be taken as R. You can check yourself that it is the case. It's not exactly the same as here, but it is similar. Can think about how it is similar. And it is also, of course, C vector space simply by exactly by the idea here, right? Right. Okay. Oh, that's a vector space. Well, let's take something more familiar. Consider R2, R3, and more generally, Rn and initial numbers. Well, let's take it bigger, equal to. We could, of course, also say that R is vector space with same structure, but well, not needed necessarily. But you can see that that one is just a showcase in case of R of that, right? And you know how it is defined. We just take addition B component wise, right? X1, Xn. You know that we just can see each vector in Rn. Well, a particular example, R3. R3, each point is just the position vector of this point. If we just take its coordinates, its z coordinate, its y coordinate, its, I don't know, x coordinate, right? So that's x, it's y, it's z. Okay, just look. Let's take this point, take its coordinates. We could call this point P or something. This is its PZ coordinate. This is its PX. That here is its PX coordinate. Right. That here is its PX coordinate, and that here is its PY coordinate, and the point itself is in PX, PY, PZ. Right. So that we just define coordinate wise addition. And coordinate wise means that we just make the separation in the coordinates coordinate wise. And xn plus y, and the customary field is of course R, so you can guess how we define for lambda in R. x1 to xn. Right. So, of course, we can do the whole stuff more generally. Find field k, for example, complex numbers or something, or rational, rational quotient functions and things like that. More generally, for any field k, define analogously vector space k plus dot with plus dot defines like right. All right. Okay. Well, what is next? Particular special case is the vector field of your matrices, vector space of matrices. Don't be confused that by matrices we don't write the things in a column. We just write them also as independent coordinates in things like such rectangles, and we just have some A11, A12. This is matrix A, right? And we have some A1, let's call it N. And we have here some AM1, and we have here some and well, if you are confused, A11, A12, I.III. So the first row, we go in the row and we count the columns A13 in the third column, A14, and so on up to A1 to the nth column, A1n, and we go to the second row. The first number of the matrix coordinates changes, and this gets A21. So we are in the first column, we are in the second row, so first number is row A21, A22, and A23, A24, A25, A26, and so on until A2n. And so we go, this is the first column, that's why we go, and here the second number is always 1, go until A and 1. And here we go in the last row, so this first number of the matrix coordinate is always kept the same, always kept M, and we go AM1, AM2, we go in the columns, first number kept the same, AM3, AM4 until AM, and this is the last matrix coordinate. And as you can see, we could just say, well, there are mn coordinates, and we could just write it in the vector. A11, A12, and you could also call that some B1, B2, and so on until AMN, which corresponds to some A to some B, just how many we have BMN, so that this is actually element of Rm multiplied by n. So matrices are nothing but vectors, and that we write, and especially because such a configuration of numbers simply allows us simple operations to appear to us intuitively. Probably you know matrix multiplications, for example, something special. We don't define for vectors in the same way, and so on. So that's just a suitable way of notation to be able to define some operations on such independent numbers in the natural way, right? And we write for that, if those numbers would be in R, and we write for that number of rows are m cross n, and we write cross here, we don't write dot, right? Because by that we mean actually in this context m number of rows and number of columns. Right, space of matrices, and you can guess that the matrices are added entry-wise. That is, well, by this notation is a short notation for matrices if they are in the same space, like R m cross n. That's element. That's how I write element in this geometric position, right? That's just entry-wise addition of the elements, right? So, and entry-wise addition means the place is kept same, the position, the size of the matrix is kept same, of course, and here stays the sum of the elements in the same position, right? A plus b is defined like that, and lambda a, well, what could it be? Of course, lambda a y a I j is equal lambda aij. Here I was a bit lazy. Right, so that's the space of matrices. And well, sorry. And well, let's consider example space of linear maps. Consider V, doesn't matter what I call it. And actually, let's don't call it V, let's call it already as something proper, what is usually called, right? Let's call it 0, 0, 1. It's weird notation, I won't explain it now, but how we have already encountered it. There's just functions from 0, 1. By the way, for all vector spaces above and for vector spaces upcoming, you can check yourself that it is a vector space. It's really not difficult. It's actually just using the entry-wise addition, entry-wise multiplication. Nothing else is to be done there, right? So and here I write sets like this. Okay, f is a continuous function, right? Then of course you can guess what f plus g is. F plus g is of course a function that again goes from 0, 1 to r, and f plus g at a number x in this interval is simply defined as, by this I mean defined. I do not always write it consistently everywhere where I define things, but I'm trying to write it sometimes at least, right? So, and yeah, all right, and well, that's a vector space. Let's call, let's see it as a real vector space. It's an R vector space. By the way, you can question why couldn't we talk about 0, 1 vector space. You can think about it. The answer is quite simple. Maybe there are even multiple answers. I just think of one. Right. All right. That's just function again from 0, 1 to r, and you just have lambda multiplied by f, evaluated at x, and that's of course lambda multiplied by f of x. So again, II.I's, and lambda is just in r. And you can think of an amusing thing which I'd like you to think about because it's really amusing. We considered those vectors, right? We had something like x1, xn plus y1, yn, yn2 is equal like this component-wise summation, right? But now let's imagine, just imagine, it doesn't have to have any mathematical meaning for you now. But just imagine that somehow we have managed to number with some weird numbers. We have managed to number all the not weird numbers, but now let's imagine our indices in the vector. They just go through all the numbers in 0, 1. This is how you could view it. You could see, you could say that f of some x in 0, 1 is actually f, which is numbered by this x. So kind of like fx is f lower index x, and you could consider that really as a real number at some abstract position x in a vector whose positions are actually numbered by the numbers in the interval 0, 1. Right, and here it goes. It's of course infinite. It's even more than n infinite, so even more than natural number infinite, more than just n infinite in many entries. You can just think about that you could actually have a funny thing. You could consider functions as such vectors if you like, right? And which are just numbered by your respective elements in the domain where the value of the function at place is numbered by this place. Yeah, that's an interesting thing to think about, right? And well, you could also just think, of course, vectors on the other hand are nothing else but just some well, let's put it like that. What is a vector? The application of that thought, another way around vector is just a function x from no 0, of course. We start by 1, right? Start our numeration by 1, right? When, and that goes to r. That's same. We just number the components in the vector, which means we assign to each of the numbers 1 to n just some component in r which we can choose, right? but of course it's a certain choice, so x is already x has fixed assignments, yeah, namely exactly the assignments. X1 is a number, right? We could say that it is like, I don't know, this is the number E, this is the number P, this is P squared, this is, I don't know, anything, ln 5 or whatever, and then you just mean that E1 is mapped by this function to E2 is mapped by this function to pi, and well, I don't know, the other I have not specified. Oh, pi squared I have specified, but it doesn't matter. N is made to mapped to L5, and you can think where the other numbers are mapped to. We just haven't called that except for pi squared, but you understand what I mean, right? So this is interesting. We have two views to consider some vector or some function. A function can actually be considered as vector, and a vector can actually be considered as function. And actually, there is no real difference. The difference is just that we are used to one notation one case, and we are used to other notation to other case. And in the case of function, vector notation becomes quite handy. But mathematically, there is no difference at all, actually. If you think about it, there's no difference at all. You could also have something like, maybe it's aside, but it takes just a very general function a, b, and we just have some kind of BA vector. So vector is just our type of, vector notation is just our type of notation, nothing else, right? Don't mix that up with elements of a vector space. That's not necessarily the case. Well, it is kinda, but we won't go into it, at least for now. It's just an interesting, funny way to think about it, right? Right, okay. Totally wanted to amaze you with that, if you didn't already know. Okay, that's nice, right? I.III. Right. Well, I think that's it for now. Other vector spaces we'll uncover when we need them. So I will specify them, define them. But yeah, I think that's it for now. Thank you very much for your attention. And well, I have to finish with something. I think we'll stop here. Okay. Thank you very much, and until the next time.